Okay, so this is the last talk of what's been a power-packed and fraught meeting, you know, in the joyous sort of way. And I stand between you and the next panel session. So what I wanted to do was, rather than do an area review and that sort of stuff, I wanted to tell you a little bit about my particular journey. That's it, and I think it obviously reflects or has something to do with our collective journey in this area. So I'm a hardhead, and what that means is that I usually take a problem and I bang my head against the wall until it bleeds, then I walk away, and then I bang my head against the wall again, and so far nothing's cracked, so the problems usually yield. And I think it's a function of the way I was trained, but I didn't, and I'm a theorist now. This is what I do. Show me a lab, I run. But it wasn't always that way. Way back when the dinosaurs roamed the earth, that's the title of my thesis. Methods of frequency selectivity and synchronization measurement in single auditory nerve fibers, application to the alligator lizard. Very, very specific, very, very wonderful. Multi-million-dollar facility, animal sacrifice, dances, all sorts of things. And after finishing that up, which was better than building spinal jumper cables, that's what I initially wanted to do. And after about 3 years, I realized that right now I'd still be a PhD student. I loved lab work so much that I went to Bell Laboratories and became a theorist, and in particular became a communications theorist after having this kind of biophysics, information theory sort of background. All right, so, Bell Laboratories, Arl has since gone. Arl and I are roughly contemporaries. He was at Columbia, I was at Bell Laboratories. We were all doing our communication theory thing, networks. And, then I went to Rutgers, or a bunch of us, once Bell Laboratories looked like it was going to become what it is today. No, sorry. Sorry. A bunch of us left and founded a wireless lab called Wind Lab. So I was doing wireless, and it was fun, and it was great, and I was just sitting there doing wireless. And then we had this problem. We realized that interference, wireless interference, is bad. And mutual interference is a network killer. Pretty standard sort of stuff. You know that. But mobility is also good. And this was before, this was when wireless was still about telephone calls. So if I'm talking to you, there can't be any delay. If you're giving me out a quarter a second, between a half and a quarter a second delay, I begin to talk like this, right? So it's got to get there right away. But with these new systems, it didn't have to get there right away. So delay is possible. Here's the other thing, and Andrea, who, I credit this work to Andrea Goldsmith, who did the first work, at least to my knowledge, on fading channels, time-varying channels. So if you couple that to mobility, I shouldn't be talking to you. If you want to hear this talk, I should go right up to Tom and hand him a chip, right? And he's got it, because he's a visual sort of guy. All right, so the other thing is the storage density is increasing, right? Moore's law. All right, so what did that mean? Wireless epiphany. Go postal, all right? And you know what that means in the semi-pun. But forget radio, write the message down, toss it to the recipient, right? Seems pretty obvious. It seems stupid, right? I mean, that we love our cell phones, and it's there's the physics. It shouldn't really dictate that we should hand out information that way. But that's where the hard-headedness comes in. Once you realize that it is, and this is a fact, if you're close, you can transmit much more information than if you're far away, for obvious reasons. If I were across the street without my mic, you couldn't hear me. It touches on this communication theory zeitgeist. And part of that zeitgeist is, put something in a truck and drive it across town. And this is from the 50s. One of the progenitors of the internet, Paul Barron, used to pack up tapes. Tapes in airplanes to send them around the world. All right, so, the hard-headedness, here's a little analytic rigor. Up here is the radio scenario. You got an antenna. It's blasting out something. It has a certain aperture, and for the electrical engineers, physicists, you know what I'm talking about there. The bigger the aperture, the tighter the beam. Same thing over here. The bigger the aperture over here, the more energy you collect. This is something that we kind of know. And then you got to compare it to writing. And writing is really very, very simple. You write it down in some medium, and you literally kick it. Okay? And it turns out that that's actually the minimum energy way to do it. Literally, just giving it an impulse. That's why rockets, when they say fire your retro rockets, they don't fire them for an hour. They fire them for a little bit. So that's what you do. You hit it, and it goes from one place to another. And then you really have to do the comparison correctly. The first comparison is there's this unavoidable delay. Things can't get there faster than the speed of light. And then the comparison you make is, if it's radio, you can transmit, but the message has to end just when the mass particle arrives. So that's the comparison. So which is more energy efficient? And you probably already know the answers to that, because if you can tolerate delay, now mind you, if I got to get it to you right away, that's impossible, right? Because you can't accelerate mass up to light speeds. But if you can do a tenth of the speed of light, or a hundredth of the speed of light, or whatever it is, a nice saunter over to Tom over here, it turns out that it's stunningly more efficient. Okay? So I haven't, not told you anything. This is kind of all culture at this point. It's stunningly more efficient than radiation. And the long story short is that published a paper in Nature, made the cover of Nature. My title was Write or Radiate. They changed it to something with ET in it. So, it got picked up by various news outlets, and it did wonders for my expert witnessing career. But the bottom line is that, and let's look at it this way. If I want to send something 10,000 light years away, radiation is going to disperse. Okay? 10,000 light years away, you do the comparison, you write things down really teensy. Let's say you write it down in DNA or RNA, or you take an atomic force microscope and arrange atoms on a substrate. You're talking about a factor of 10 to the 15th. And just so that you get a feel for that, if I took a sugar sack and lifted it up onto a shelf, let's say that's the amount of energy that it took to do the mass, to send the message, the corresponding amount of energy to send the same message would be like detonating, I think it's a 24 megaton bomb. Okay, so it's not a little bit of energy, it's a lot. And when nature shows you a lot of energy, an energy difference like that, you begin to think, well, oh, and we also got an NSF mention on the Discoveries page. Is that still active, NSF people? Do you still post to that? Nah, it's ancient. This is when the dinosaurs roamed. Okay, so here's the clearly logical conclusion, right? So, I had this fantastic success in looking at a system that wasn't a wireless system, but it was a wireless system. And, inscribed matter is energy efficient. We all know, as the engineers among us and the physicists among us, propagating electromagnetic waves in fluid, especially salty fluid, sucks, right? Doesn't work that hot. So, wait, biology uses inscribed matter already. I mean, that's really what this meeting is all about, right? You transport things around, actual physical things. It's not waves usually. So the obvious, logical conclusion there is, I speak as a communication theorist. Biology must yield to me. Okay? It's my oyster, and it'll do so by next Tuesday. Okay? All right. So we got together, wrote this proposal to NSF. This is when was it? A long time ago, 12 years ago. And look at it. It's really kind of cool, right? So there's Drosophila, there's Christine Nusslein-Vollard, their Nobel Prize, and I said, yeah, I can get some zebrafish, I can get some flies, I can do this. When you actually start taking apart, going from blastoderm to near fly, there's scaffolding. It gets picked up, it gets torn down. Stuff moves around. They don't know what's actually there. And the assays are ridiculous. It's really kind of scary. So, that's me. After a little while working there, and what you do, when you're, as a communication theorist, if you're faced with a system that you just can't really handle, you can't get your hands around, what you try to do, and this is what the physicists here do and what all the communication theorists here do, is you try to get your hands around it and provide some inviolable bounds. So that's what I spent a bunch of time doing. So seeking inviolable bounds, outer bounds. All right, so here's a cartoon of one of the things that we've been talking about. You've got something that's emitting particles. Right now, they're all identical particles. It's emitting particles. As Max said, there's some sort of transport mechanism. to get the particles from here to there. I don't really care what the transport mechanism is right now. They get there, and then there's a whole bunch of, there's the Purcell paper on sensing, right? So, you got a sensor here, it either binds, doesn't bind, all sorts of physics there. That's too hard for me, okay? And the reason it's too hard for me is that the Purcell thing is hard. Plus, when you're thinking about it from an engineering standpoint, one of the things that we like to do is we like to steal from biology and do other things with it. So that particular way of doing the sensing may or may not be a good thing. So what you have here now is we have a slightly different scenario, less realistic. We're emitting things. They reach the receiver, are captured and deactivated, okay, taken out of the system. So once you have that, what we have is we have emission, and the only thing that we know about the emission is there's emission times, and the only thing we know about capture is that there's capture times. Those are the things that we know. And the fundamental problem is, how do you get information from the emitter to the receiver? Still not simple enough. I shouldn't say it's still not simple enough. This is a little bit of a twist. One of the things that's a problem is that you all know particles persist. Right? So a neuromuscular junction, if you just release that acetylcholine and just kind of left it there, you'd be kind of screwed, right? You got to go in and cholinesterase it out. So you could imagine trying to kill particles in some sort of way, or letting the particles themselves denature in some sort of way. So that's another model that one could use. What I want to emphasize here is that these are outer bounds. Any physical system that's communicating in this way, meaning releasing stuff and having it taken up somewhere else, that's this model, and this provides an outer bound, an upper limit for the capacity. So whatever you do, put all sorts of twists and details in there. If you're emitting things at a particular time, identical things, and picking them up, that's the fundamental model. The only twist that I had was that I remove them. I don't let them sit around once I've received them. The other thing that's a little bit annoying is that diffusion in free space, right? The particle may not get back. And that wreaks havoc with something that I'm going to bang on pretty hard. And here's the generalization where you got a whole bunch of different particles. And this is a cartoon. These different particles could be different molecules, could be different strands of an oligomer, could be whatever, but they're different. They're identifiable at the receiver. Same drill. They're in a boundary so that they can't get out and never get there, so they always get there. We pick them up at the receiver, and we do something with them. So that's the fundamental model that we're going to be working with, that one there. All right, so now here's where you go down the rabbit hole. So when this work first came out, I think Ian we were contemporaries in this. So what Ian immediately did, Ian Achildes, what he immediately did, he looked at concentration. And just like Max was saying, it's a nice linear system, you can play with it and do whatever. And I looked at that and I said, wait a second, it's concentration. And the concentration is of particles. And if I'm not dealing with particles, I'm not dealing with the fundamental problem. So, 10-year-old full professor, I just couldn't be intellectually honest and just go only that way. So I went this way. So I started playing with explicitly this model with particles and picking them up as opposed to concentration. And the reason is that this is the finest grained version of that. An information theorist in the room, data processing, done. Okay? Whatever you get here is less than or equal to what you get over there in terms of capacity. And I'm going to define these things more carefully because I think that that's important. One of the things that I think has happened at this meeting or has been illuminated is that sometimes we're talking a little bit at cross purposes. So I'm going to be very kind of information theoretic with the knowledge that we need to find a way to bridge what it is we think we know. All right. So once you understand timing, you're done with this channel. You know what the bounds of the capacity are. And you can twist it and tweak it and do whatever you want, but that's the fundamental bound. Okay, so here's my Hardhead's unified framework. Timing's fundamental. Payload's fundamental. I throw this figure up here because that was part of the Nature paper, or one piece of the Nature paper, where you have to ask how densely can you write material in matter. And I literally spent 6 months trying to and this is the banging the head thing. So this way I came away bloody, and luckily I walked away, trying to rederive Bekenstein and Hawking's result on black hole information. And you know, it didn't work. In any case, energy use is fundamental. We haven't talked about that yet, but you know, biologists, information theorists, we all care about energy. And here's the block diagram for the channel now, for those of you, that care about these sorts of things. So you have the times of release of these identical particles. Remember, we're identical particles. And here's what I think is the joy of this particular model. We're going to assume that the particles travel independently from the source to the receiver, okay, under some stochastic process. We characterize that stochastic process, meaning all we know about is the time of arrival, and I'll get to out here in just a second, and the times of departure. That's the best that we can possibly know. So for each particle, there's a particle along this rail that I release, and I'm calling this a rail for a reason. It's not a, don't think yet in terms of the physical model, but there's a rail. I release a particle here. It takes some time to get to the destination. It gets there. Now, what do I see at the destination because the particles are identical? I see an ordered list. So it's possible that this one took a long time to get there, this one took a short time to get there, so that out here, the thing that I sent on this rail appears up here, whereas this one appears after. Okay, so there's some sorting going on. Again, this is fundamental. You can't get around this. This is a fundamental model. Okay, so let's analyze it a little bit. And those of you that play with this sort of stuff, you already know where I'm going. So this is an additive channel. We like additive channels. We like them a lot. Times of release, that's a vector. Times of release, times of sojourn, how long it takes in the network to get to the receiver. And those are the ordered, or those are the arrival times. This S corresponds to here, so that if we knew S1, then we know that it came from T1. So we have one more step to do. We have to do an ordering operation. Okay? And the only other thing that we care about in this particular model, we care about the statistics of D, okay, each one of the individual passage times, but we're also going to restrict D to be some average, the average D to be less than some number. Can't be infinite. Okay, so here's something, I gave a talk at this thing once, and they had these lovely displays that showed you exactly how much time. So it feels like I haven't spoken at all, but I probably used up 15 minutes about. So keep me on time is the point, because what I don't want to do is 10 more minutes. Perfect. And you'll laugh when you see what comes next. All right. So departures. One cool thing is that I could reorder those rails, and it doesn't really matter. So there's some mathematical cuteness that you can do that allows you to analyze the channel. Now this one I want to spend a little bit of time on. What very few folks do, not everybody. Ubli's pretty careful. Nariman Farsad's pretty careful. Others, Max is pretty careful. What you do is you got to have channel uses. That's a fundamental thing with information theory. So it's not like, oh, I used the channel and I transferred information. No. I mean, yes and no. The mutual information bound that we all know and love is, what's the term you, Michelle, everybody? Asymptopia. Okay, we live in asymptopia, where we use these channels a number of times. There's a block length, and we have some results, hard and fast results. So that's a big deal. So what do you have to do? The first thing I have to do is I got to make sure that the channel uses are independent, and they're not independent if I got bleed over from here to there. So what I have as a picture here is the signaling interval, where I'm laying down all the stuff. Here's a gap where stuff takes time to arrive, and what I'm going to do is mathematically, or set up as not as a proposition, as a requirement, that everything arrives before this guard interval is over. And that's a standard sort of thing. And information theorists, if Arl were here, he might beat me up. If Georgios Giannakis, who you don't know, were here, he might beat me up. But it's not, I could defend myself pretty well for that. So I'm defining some things. Here's the average rate at which I dump particles into the system, m over the signaling interval. I already told you what the expected value of the departure is. I'm now defining this thing called a power constraint, where it's the number of particles per unit time, because I'm assuming that it takes a certain amount of energy to build these particles. Mostly these things get transported for free, but even if it doesn't get transported for free, as long as each particle costs the same amount of energy, that model still works. All right, so limiting details, blah, 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 blah. Here's what you care about. Everything's okay if the expected value of the arrival time exists. It's not okay if it's not. You don't have a patent channel model. So you can't use straight old diffusion. You got to use diffusion in a box. So that's one of the things that I wanted to mention is that Nature paper was great. It talked about we should be looking for artifacts from beyond. I can't get into all of that. But what it does provide is physically inviolable results. And this is one of them for this system. I'm saying something semi-bold. If this is not finite, you don't have a patent channel model, so you have no business talking about mutual information and capacity. So it got very serious there. All right, so wait. If I find a bunch of systems, I find a bunch of things. Here's the capacity per particle. Here's the capacity per unit time, but it's a funny sort of unit time. It's per first passage time. It's normalized. Physics people like that. I like it. And this is why I was going to make you laugh. So I have 10 minutes. La. Let me just do this. So those of you that do information theory, forget about everything else. You look at this. There's mutual information, entropy of S minus the conditional entropy. We know how to do that. That's easy. We know how to solve that problem. That's the typical additive channel problem. It's easy. Done. No, it's because the reordering. So you end up with order distributions. I'm terrified of order distributions. So I did something slightly different. What I did was I noticed that S, the arrival times, and then the ordered arrival times, and then a permutation number, these two things are equivalent to each other. Lovely information theory, you end up with something that looks like this. That it doesn't really matter. It's just a trick. All right, so what does that end up doing for you? Now, to maximize this, you got something over here that's a constant. This is easy. And then you have stuff that you need to maximize. We kind of know what to do with this. It's not an order distribution. It's on the original S. This we got to actually calculate, but it turns out you can calculate it for certain situations. There is a tension, though, as you can imagine. You want to maximize this, it tends to depress that. You want to depress this, maximize this, it tends to depress that. And I can give you examples. All right. So we got to have a power budget. Identical particles, as I said, we're just going to assume a certain amount of energy per particle. Don't care what it is. I'm going to throw ATP at you up there, but it doesn't really mean anything here. Here's another thing that's a little bit I want to mention. So you could imagine now particles that are not just by themselves, but they're oligomers. So they are identifiable, right? Because once you got the oligomer, you can tell one from the other, as long as it's not the same set of bases. But there are other ways to embed information in this context. I could send a sequence of known certain lengths of oligomers that encodes the information. Now, why am I worrying about this? Because now what I'm going to do is here, instead of identical particles, I'm going to send particles that have information embedded in them. And at the receiver, I could send you for example, I could take this sheet of paper is a bad thing. I could take a book and chop out all the letters and throw them at you, right? And read the book. Can't read the book. You got to sequence them. So you need sequencing information. And the machinery that we developed allows you to tells you what the sequencing information has to be, the minimum. All right, so, blah, 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 blah. You don't care about that, but this you do care about, or you should care about, within reason. So you do all of that, and if you use exponential first passage, which is not something that people generally do. Usually you think about diffusion, there's the, the inverse Gaussian, blah, 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 blah. Nope. This one analytically worked and, seemed like it was reasonable. Plus, the exponential distribution in this particular context has some max-min properties. So what you end up with is you can derive a lower bound, and this lower bound says that as you increase the number of particles, the information rate, this is in nats per passage, goes up. But then this actually does flatten out. It goes to a half. So what this means is if you use this particular method that I didn't tell you about, but if you use this particular method of transmitting your particles, choosing your code book for the information theorists in the room, this is kind of depressing. Now here's the really depressing part. I've tried a lot to make this thing just a little bit, raise the lower bound just a little bit. It has not budged. But then you have Max, who did the early concentration work, and he showed you could get some ridiculous bit rates using a concentration model. So, you know, there's something going on here that we need to figure out. But then there's this upper bound, which is a general upper bound, and that scales. And this is semi-exciting. Theoretically, it's really exciting, because this is particles per passage. And when we're talking about molecular systems, we're kind of talking near Avogadrian numbers. You know, 1 billion less than Avogadro is what, 10 to the 15th? Right? So, you know, this is per passage. Even if per passage was a second, if you send 10 to the 15th particles per second, identical particles, meaning you don't have to structure them, that's a very high bit rate. So that's kind of interesting. Then there's the particle sort of thing. The identifiable particle, where you're putting a payload onto the system, onto the particle. These are just for comparison. Those are identical particles, but we're using parallel channels, maybe 4 different particles. And here, the payload channel, that does increase. So that's the punchline here, right? Payloads seem like they might be a good thing. The jury's a little bit out on the identical particle channel, but if I had to bet this finger on the identical particle channel, I'd say you don't want to do it if you're trying to increase your data rate. And if you have a system that uses identical particles via timing to signal things, that may tell you that there's a certain data rate that you can hit, or there's a limit. All right, so you know you should be awed at this point. And are we there yet? So I dragged myself semi back into the lab. I have a collaborator, Jacob Rosenstein. I can only work with people named Rose, apparently. It's a short but long story. Built a system, and this is the souped-up version of Andrew Exford's alcohol experiment, where he blew some vodka. We didn't use vodka, but we used alcohol. So you did this. You got these high-priced sensors. They're ion detectors. You know, they suck the thing in, ionize it, see what's there. And we're blowing things in, we're injecting things, we got a whole control system. The mean first passage time is on the order of 1/10 of a second. Calculate the number of particles that we're using in each puff. Now mind you, we didn't try to control the release of each particle, but you know, we got up to a whopping 40 bits per second, you know, after all that effort. So, you know, we're nowhere near where we could potentially possibly be. And that's where I think, for me at least, that's where the excitement is in all of this work. All right, so the summary is timing alone, the upper bound's tantalizing. You need a lower bound raised because it seems to asymptote out for Avogadrian joy. I can't find anything linear in scaling for the lower bound. Timing plus payload, it does scale nicely. And I didn't mention this, but obviously there's a trade-off between the amount of sequencing information and the amount of payload information. But you know, that's doable. And here's the only question, not the only question, but a question. Should it be a temporal string of pearls, you know, little tiny pieces? Or should you send things out in one big blob, you know, send it out in one big library? There are engineering reasons why you don't want to send it out. You know, it's hard to synthesize things that are very long. It's easier to synthesize things that are shorter. So that's an engineering sort of question. But the information theory seems to have spoken. So what's next? I want to chase Avogadro, raise that lower bound. That would make me really happy. I want to look at the payload trade-offs, and you know, this is what the community should do. MIMO should be really interesting, where you now do spatial stuff. And then there's the multi-user thing, and that's really intriguing to me, because you can imagine now, so you know, the other Chris Barr over there, and we're talking, and maybe we have different temporal signatures in the way we release things, and that's how you tell us apart. So that's that. And now for this specific meeting, you know, so I can't call it advice, it's just observations. So, you know, I guess one of the things that comes around is that I think we need to figure out what information is. Who knows what's information? Enumerate what you care about. Identify important variables. Okay? That was for emphasis. Figure out what your channel use discipline is. And then for the rest of us, meaning the physicists and the comp theorists, we should still seek outer organizing principles. You know, a cell wants to become this or that. How much information does it take? How do we transmit it? Identify the conditioning. Once again, this is actually the same question. okay? Because there's this much information in the genome, but most of those genomes are not viable. So if you condition on being viable, that's less information. And the last thing is always show humility. And with that, thank you.
We got time for a quick question.
Okay, then.
A broad question and a narrow question. Back around slide 30, you had m. And does that mean you're sending the same number of particles each time? That m was a constant? That's the narrow question.
Yes, that makes your life easier, but it doesn't have to be.
Okay. Broader question. When you look at signal transduction systems, you see lots of use of simple molecules, which would be like your,
Nitrous oxide, go ahead.
Yeah, so if I inscribe, then I have to decode. And there's lots of simple receptors, right, for each of these different transmitters. So it looks like nature has chosen, in some cases, to do what you were recommending against.
Right, but it's also chosen to do what we're recommending for, say, some, right, because, well, nature does it, right? It depends upon what. Depends on what the context is. But here's the way I look at it. So our nervous systems are great, right? And they're wonderful as opposed to an endocrine system. If your endocrine system had to warn you about a lion, right, not a good thing, right? That's probably not. You need nerves, okay? You need a brain, and that's energetically costly. So I'd say biology does it the way it needs to do it. What I'm providing are bounds for whichever method you use. Reasonable, Peter? Yep. Okay. Ubli?
1.5 questions. So I'm intrigued to understand how dependent your results are on this notion of ordering and sorting. And I'm wondering if that is what is perhaps giving you a loose achievable rate. And then related to that, you have this experimental system. How does that connect to the achievable rate? Like, is it in between those two curves, or not?
So I'll answer the second half question first. That system sucks compared to the achievable rate. Oh, excuse me. We can't call it. I can't call these achievable rates. Remember, because the thing flattens out, right? So you end up with 1 bit per. It sucks. It truly sucks. It just sucks. As far as sorting. So you'll help me with this. If I have identical particles, and what I'm doing is releasing them at a source. Now, yes, I'm assuming all the things that all the biologists and everybody else hates. There are clocks, and so we know, but you can loosen that up. That's, you and I know that that's like a one-time sort of deal. If I'm releasing things and somebody's receiving them, those are the only 2 things that I have. So by definition, they're being resorted. So maybe I missed your question.
I think the issue is how you wish to convey information, right? So I think there's a price to be paid to do the registration of who comes in what order, which is part of what your result is getting at. And I'm just curious as to how much of a price you pay. And because I'm kind of like Max in this, I like the concentration issue or approach because it means that I don't have to worry about that.
So if
And I understand you're trying to figure out what the maximum amount of information
I got the question now, okay. So I'll make it stark. So if that asymptoting thing for the identical particles is the actual upper limit, then we have a conflict because the concentration thing is getting way too high a rate.
So I don't think it is. I think it's a feature of how you compute your bounds. And we all make, our inequalities go in a particular direction to get a result. So somewhere in there's an inequality that got invoked that is costing you too much.
So if the asymptotic thing is wrong, meaning that there are things that are above, then we're okay. So that's the flip side of it. If there's something that scales more or less with the number of particles that you send, then we're good. But I'm just saying that there are these 2 things, and I have not been able to use the particle system to get something in between.
I believe we are good.
All right. Good enough.
Okay. So thanks. We have a last breakout. So.
All right. Thank you.